All right, welcome back. So last time we put together the heart of our microbial fuel cell, the anode. But you know, a heart's not much good without a system to pump blood through. Today, we're building that system. We're going to complete the circuit, and we're going to do it by focusing on the other essential half, the cathode and the membrane.
Okay, let's just jump right into it. You've got your anode, and it's buzzing with electrons thanks to our little microbial buddies. That's awesome. But right now, those electrons have absolutely nowhere to go. See, an anode by itself is just half of a battery. To get any real power, we have to give those electrons a destination. A circuit is only as strong as its final connection, and that's exactly what we're building today.
So, the very first piece of this puzzle is the cathode. The easiest way to think about it is as a landing pad. It's the destination for all those electrons that have traveled from the anode through our external circuit and are ready to finish their journey. This is where the electrical part of the story ends and a really critical chemical reaction begins.
Now what happens at the cathode is just fascinating. It isn't just sitting there waiting, it's an active chemical engine. And it's all driven by something called the oxygen reduction reaction, or ORR for short. This is where the magic really happens. The cathode grabs oxygen right out of the air, it takes protons that are coming over from the anode chamber, and it accepts the electrons from our circuit. It mashes them all together to create simple, harmless water. This reaction is the engine that literally pulls electrons through the circuit, and that's what generates our electrical current.
Let's break that down real simple. First, oxygen from the air just kind of seeps into the porous material of our cathode. At the exact same time, protons, those are the positive hydrogen ions, they're making their way over from the anode. Then, our electrons, after they've done some useful work like lighting up a tiny light or charging a sensor, they arrive through the wire. Finally, all three of them meet up at a catalyst site on the cathode and bam, they combine, they form water, and that clears the landing pad for the next wave of electrons to come in.
So the big question is, how do we build a cathode that does all this as efficiently as possible? Well, the performance of your MFC really, and I mean really, hinges on the materials you pick for this part. A poorly designed cathode can become a total bottleneck for your entire system, and it won't matter how amazing your anode is.
For the best possible balance of performance and cost, we're going with what I like to call the cathode dream team. First up, our base material is activated carbon. Second, to really kick that ORR reaction into high gear, we need a catalyst, and we're going to recommend an iron-based one. And third, to make sure our cathode doesn't get all soggy and stop working, we add a waterproof layer of PTFE.
Why activated carbon? Just look at this number. Up to 1,500 square meters of surface area per gram. That's insane. It's like taking a whole football field's worth of reactive surface and cramming it into something the size of a sugar cube. This huge area gives us countless microscopic landing pads for that oxygen reduction reaction to happen, which totally maximizes our power output.
And you know the best part? Building a high-performance cathode with this dream team isn't going to break the bank, not even close. You can get all the materials you need for somewhere between $5 and $15. And it'll give you performance that rivals super high-end materials, but at a tiny fraction of the cost.
But of course, our recommended build isn't the only option out there. Like any big engineering decision, picking a catalyst is all about trade-offs. You're constantly trying to balance how much you want to spend versus how much power you're hoping to get out of your fuel cell. Our recommended iron-based catalyst really hits that sweet spot. It's low cost, but you get excellent performance. Now, if money is no object and you've got deep pockets, you could go for platinum. It's the gold standard for sure. It'll give you about a 50% power boost, but man, is it expensive. On the flip side, if you're on a super tight shoestring budget, you could use something like manganese dioxide, or MnO2. It's dirt cheap, but you should probably expect your power to drop by about 20 to 30%.
And this chart here just makes that trade-off crystal clear. We've set our recommended iron catalyst as the baseline, right in the middle. You can really see the huge jump in power you get with platinum, but you can also see that noticeable dip you take with the budget MnO2 option. For most projects, iron is the clear winner when it comes to value.
Okay, cathode design, check. But there's one more piece we need to consider. It's the bridge that connects the anode and cathode chambers. I'm talking about the membrane, and whether or not you even need one is a really critical choice for anyone building an MFC.
So what in the world is a proton exchange membrane, or PEM? Well, it's basically a specialized filter that you put between the anode and the cathode. Think of it like a bouncer at a really exclusive club.
It has one very specific job. It lets the protons right through, no problem, but it blocks the bigger molecules, especially oxygen, from sneaking into the anode chamber where they could cause trouble for our anaerobic bacteria.
So here's the big decision you have to make. Are the benefits worth the costs? On one hand, you can go without a membrane. This is pretty common in simple, single-chamber designs. It's cheaper and it's definitely easier to build. The downside is you'll have lower efficiency. On the other hand, using a membrane, like the popular brand Nafion, is more complex and it costs more, but it can seriously boost your cell's efficiency and help keep the pH stable, which keeps your bacteria happy and productive.
And when I say a boost, how much are we talking about? We're talking up to 90% coulombic efficiency. Now that's a fancy term, but what it basically means is that 9 out of every 10 electrons that your bacteria produce are actually captured and sent to the circuit to do useful work. Without a membrane, that number can be a lot lower. So, if maximum power is your goal, a membrane is absolutely the way to go.
Phew, okay, we have covered a ton of ground, right? From chemical reactions all the way to material science. So let's bring it all home and wrap this up with the key takeaways for finishing your MFC circuit.
So here it is, your blueprint. For your cathode, that dream team of an iron catalyst on activated carbon, waterproofed with a PTFE layer, is going to give you the best bang for your buck. For the membrane, remember, it's optional, but it's highly recommended for those dual-chamber designs where you want to squeeze out every last drop of power. The choices you make here are what will directly impact your final power output. And hey, don't forget the practical stuff. That PTFE layer is your best friend for preventing flooding, and making sure everything is sealed up tight when you assemble it will save you so many headaches later on.
And with that, the circuit is complete. You now have the full design for a high-performance microbial fuel cell, all the way from the anode that makes the electrons to the cathode that accepts them. The blueprint is in your hands now. The only question left is, what kind of power are you going to unlock?